This video will show you how to use the HOSI GUI. That's the graphical user interface for this hyperspectral open source imager. So first off, you need to set up your working directory. And in there, you'll need everything shown here. So you'll need the HOSI GUI Python script itself. You'll need a directory called scans, which is where your scans are saved to. You'll need this grid basic file. And then you need these two important files of the calibration data and sensitivity data. The calibration data shown here, so this is a text file with unit-specific information. So here we have 9 being the unit number, and then the type of data, so wavelength coefficient data. And here we have the coefficients which are supplied when you buy your Hamamatsu chip. It comes with the information about for each photo site, which wavelength it is sensitive to, and this is the coefficients that describe that. So that will be specific to each unit. Also specific to each unit will be this radiance sensitivity information. So you need to ideally measure your system relative to some known radiance. So use a spectroradiometer that has been calibrated itself to measure some light source, measure that same light source with this HOSI system, and then you can use the script to calculate these radiance sensitivity data. They vary a bit between units. How much I can't say because I haven't calibrated quite enough, but you should assume that the calibration is not perfect by using these data that I'm supplying. Also then you have the linearization coefficients. So the sensor tends to be quite linear, although that linearity breaks near the 0 point, so near the dark measurement, and actually that becomes quite problematic for some scenes with lots of dark stuff going on. Or darker parts of the spectrum, I should say, rather. So that's quite easy to work out, though, and that can be worked out per unit quite easily. Okay, next we have in here the sensitivity data. So this is a spreadsheet, a .csv spreadsheet that we can open up here. And in this spreadsheet, the first row is just the wavelength data, so from 3, in this case, from 3 to 800 nanometers. And then we've got some base information that the system needs. So first we've got the chlorophyll values used for the NDVI index, and we have the CIE X, Y, Z functions. But you can also add your own spectral sensitivity information here. So I've added blue tit spectral sensitivities, long, medium, shortwave, UV, and double cone functions, and also honeybee, medium wave, shortwave, and ultraviolet. The data here are just normalized so that the area under the curve is 1 for each channel to give them equal weighting. So that's the sensitivity data. Next, you need to load up your this HOSI script in a Python environment. So here I'm using Genie, a nice lightweight Python environment to work with. Load up the script, and you'll notice that you'll need some libraries to get this to work first. So this script you can either run on your Android phone using PyDroid 3, and in that environment you need to install these libraries: matplotlib, USB4A, and USB serial 4A. Depending on your environment, you might also need to install these other things. So Tkinter, NumPy, Pill, some of these are installed as standard. Matplotlib, and then so for Android only, you need this USB 4A and USB serial 4A, but for Linux, you just need this serial. So that's your environment. Once that's all set up, you should just be able to run this. So plug in your HOSI system via USB and just run this script. If you run into any errors running the script, most likely thing is that the serial port isn't communicating properly. So outputted in the terminal here is showing all the serial ports that can be read, This system is set up to just select whichever is the last on this list. But if you know which that is, you can specify that manually as well. So this is the one it is chosen, which is the last on the list here. You can tinker with the code if that's not working correctly. But here we have the GUI, the graphical user interface. So I'll go through each of its functions. First we have these buttons here, and the start starts taking a scan. We can load other scans, and we can change the image type, the color types being shown. When we're taking a hyperspectral image, the stepper motors control the pan and tilt axes, and so we can specify the leftmost point, so the pan axis left point, which is here we've got -20, and then going to the rightmost point +20, so that's the tilt axis. And the resolution of the tilt axis here are currently 4 steps. And the units of all of this is in steps. The stepper motor that we're using typically has about 2048 steps for a full revolution. It does vary a tiny bit depending on the gearing, so you could check that for yourself, but that's what I tested my system to have. So that's the horizontal, and then we've got the vertical, the tilting angle. So this is the topmost point and the bottommost point, and the resolution in that plane as well. So we can specify horizontal and vertical resolution independently. And if these buttons let us move the HOSI pan tilt mechanism to whichever is the coordinate. So the top left, top right, bottom left. So if I click this, the HOSI should come to life and move to whichever point is at the top left. And if I put that to -200 and click again, it will go to -200 or back to 20. And I can make it go to the bottom right point. And this will give us an idea of what the image is and what is being framed. And then get it to go back to its start position by clicking this middle button. When we change the resolution here, this little output thing will tell us the resolution of the output image. This will be 11 by 11 pixels. And if I just do a really quick initial scan just to check it works, so a 5 by 5 pixel image to start with. I'll just give this a label test. The maximum integration time here in milliseconds is 2000, so that's 2 seconds. The boxcar, that specifies the spectral binning. So if we had this at 1, that's no spectral binning, and that's the highest spectral resolution. If you put it to 2, it sort of saves some data without losing much spectral resolution. It combines the neighboring 2 pixels on the sensor. And then we've got our dark repeat. So this is taking a new dark measurement every 120 seconds. So every 2 minutes, that will take a new dark measurement. That means that the HOSI system puts the sensor back down into its housing, records the dark current, and carries on. Then we just need to press start if we're happy with all those settings. So we'll start and take a scan. It starts off by just initializing the sensor, so clearing out those photocells of their charge, taking a dark measurement, and then actually starting the scan. So you can see it scanning back and forth. At the moment it's just measuring this tabletop under an LED light, so nothing particularly interesting. And I can click on any pixel and it will show me the radiance output as measured at that point. So here we've got the table, a mix of LED illumination and some natural light coming through the window. And this pixel is sort of pointing out the window a bit, so this is more natural light with some Fraunhofer bands. Yeah, and this is every pixel I click on, I can see the candelas per meter squared, so the luminance of that. So it's a human metric, obviously, and the location of that, the XY coordinates. And this is useful information if you're sort of framing a shot in low resolution first, and then take a high resolution scan of it once you know exactly what's where. That's quite useful. But I can also highlight some other functions in the GUI, so we can load different scans. Let's load this docs image, for example. So this was a scan taken of Falmouth docks, and you can see it's very, there's just a few bright lights which are showing here, but we can change the brightness to see everything. And this is where this incredible dynamic range comes in, being able to take, for every pixel, we've got full spectral data at a really good dynamic range. And I can click on a pixel now and it will show me the radiance information. So if I click this pixel, this is clearly an LED light source. And if I click on another one, that looks like a high pressure sodium light source. And this one looks like a halogen light source. And if I just want to extract these spectral data, that's actually really easy. All we need to do here is I can write halogen and then click export spec. And then let's click on that high pressure sodium, and I can write in HPS, export, and then how about this LED export spec. And if we go back to the scans directory, now next to this, so this is the hyperspectral image itself, and we've got a new file next to that called docs_radiance. And if I look in this now, it has exported just those pixels that I have labeled. So we can export data really easily from this system. So I can just plot this. Oh no, scatter plot, there we go. And here we've got the absolute radiometric data for these different light sources. So obviously dominated, the HPS is the brightest, so if I delete that we can see the halogen and the LED more easily. Okay, so there are other things we can do though. For example, let's load a forest scene. So this is a woodland, an autumn woodland scene that was measured. This is about a 20-minute scan of the full hemispherical scene. So this is a 360-degree wide scan going right up to the top here. And you can see how it interpolates. It would be wasteful to measure at full horizontal resolution when the system's pointing right up. So it interpolates like this for a more efficient scanning system. And so here we have a tree next to us with some brown leaf litter under it, and we can look at the spectral radiance information there. But here we can also look at different just viewing outputs. So here this is RGB at the moment. If I click this button, this changes to saturation. And look, there's a red pixel here. That means that this pixel in red, that was too bright for the system to handle. So this was a bright sunny day, and that can oversaturate the system. So if I were to click on this pixel, the system has detected that some of these pixels have gone above the saturation threshold, which can in many other systems be very difficult to detect, but in this system it highlights it for you nice and easily. All the other pixels look good, but that should flag that you should be wary of measuring anything that is saturated in the scene. The unsaturated pixels in the scene will be completely unaffected and will be absolutely fine. So if we click on a pixel nearby, you can see that maybe we are getting around here some leveling off. Okay, so next we can put this into a different mode. This is IGU, so this is showing us an extended spectral range, infrared, green and ultraviolet in place of red, green and blue. And we can also change this to NDVI, so this gives us an NDVI index score for each pixel. Or back then to RGB. And if we load up another image, let's load up this butterflies image. This was a scan of some butterflies, and so because these butterflies were very close to the system, I needed to refocus the HOSI system. So screw the lens out further away from the sensor for measuring things that are are quite close, just a few centimeters away from the system. This was illuminated by a horrible spiky light source, a full spectrum exoterra light source that does give off UV and full spectrum emissions. But if I click on some points here, you can see it's a very spiky light source. But in this scene, I did include this grey standard. This was a 10% grey standard. And so if I type in here 10, and I'll select a pixel on this grey standard, and now click Set Reflectance. Now this is giving me everything in reflectance relative to this grey standard. So now if I click on this grey standard again, if I click on the same pixel, it will be exactly 10. But if I move this around, you'll see it's measuring about 10. Getting a bit noisy in the infrared where the light was giving off less reliable, very spiky infrared output. So this is cool, and if we can go back to viewing this image in different ways, but now it's in reflectance mode. I can click on any pixel and look at the reflectance of that pixel. So here is the yellow butterfly or the orange butterfly, etc. So we can click on anything in the scene and look at its reflectance relative to this grey standard. So this is critical. The reflectance values here are only meaningful if the light falling on the standard is the same as the light falling on the subject, which catches out a lot of people, including scientists. Okay, so we can also view this scene in different spectra. So here's saturation, no pixel saturated, that's good. And here we're showing this extended spectral range, and look at this amazing blue on the fringe of this butterfly. So this is an iridescent spot, which is only really visible in ultraviolet. And if I click on one of these pixels, we get this very interesting reflectance curve. Look, this enormous UV peak, which we humans can't see, and then just a grey background. So this is a very rare colour in nature, and will be part of this butterfly's mating signalling system, most likely. What we can also do is output what this would look like to a different system using these cone catch data. So we can see how this would look to for example, a blue tit in long wave, medium wave, short wave, and ultraviolet. So just select any channels you want to output, and then we will go export images. And once it's done doing that, we will have these new images created here. So here we've got the double, long wave, medium wave, short wave, and ultraviolet. And these images are readable in image J, for example. So if we go into image J, we can select these images, open them all up, and these are 32-bit cone catch images now. So this is the double cone, and we can turn this into a stack. So images to stack, and so here we've got the ultraviolet. I can change the brightness of this to show you what it looks like. The ultraviolet cone catch image, short wave, medium wave, long wave, and double cone. And then you can use all of the the micro toolbox related things for cone catch images, and so on. So a nice, straightforward, easy way of getting cone catch information out of the Python system. Once we have selected the reflectance standard in our image, where previously if I clicked on any pixel and exported the spectrum, it would record radiance. Now we've selected a reflectance mode. This will export reflectance instead. So if I want to record this UV patch on the butterfly wing, I could write in UV here and export spectrum, and then compare that to the white patch here and export spectrum, and maybe the yellow patch on this butterfly, export spectrum. If we go back to the directory, the scans directory where that file is saved, so here is the the butterfly's the hyperspectral image itself, a 13 megabyte, quite large image. Here are those cone catch values we outputted, but now we've created this reflectance spreadsheet, this CSV file. If we open this up, it will show us those points that we've just measured from the image, so we can output those reflectance things. So here we've got the wavelength and the UV, white and yellow data respectively. Here we go. So I can select all of this and create a chart of these reflectance data. And it gets very noisy in the infrared, so let's just make it a 300 to 700 nanometer range. And there we've got this incredible UV peak for that butterfly versus the yellow reflectance and the white reflectance. That's it. So that's kind of an introduction to the basic functions of the HOSI graphical user interface.